So this is a proof of Lagrange's theorem, which is a key result from group theory, relating the order of a finite group to the order of its subgroups. So Lagrange's theorem states that for a finite group G and subgroup H, the order of H divides the order of G. So let me put that in notation. So order of G divided by the order of H equals K, where K can be any positive integer. So let's illustrate that with a concrete example. Take a group with order 12. What Lagrange's theorem tells us is that the order of any subgroup must be a factor of 12. So 1, 2, 3, 4, 6 or 12. And for example 5 or 7 cannot be the order of a subgroup of G order 12. Now you have to be a little bit careful here, because the theory doesn't say that necessarily every factor of 12 will have a subgroup with the same order. So there is a group of order 12 which doesn't have a subgroup of order 6, for example. Now we're going to prove Lagrange's theorem by looking at cosets, which are particular subsets of G. So here's a coset. So let's construct a coset. Here's the group G, and we'll describe G like this. So G will describe the elements of the subgroup H first, H1, H2, H3 to Hn, and the remaining elements of the group which aren't in the subgroup, G1, G2 all the way to Gm. So here we have the subgroup, big H, and all the elements of the set are the elements of the group. So just for clarity, with the way I've drawn it, the order of G will be n plus m. Now to form a coset, we take any element of G, so we'll take G1, and we multiply it by all the elements of the subgroup. Now we can do this multiplication on the left or on the right, and on the left we have left cosets, and on the right we have right cosets. This proof will just use left cosets, but it works equally well with right cosets. So let's take the left coset of G1, and we have G1 H1, G1 H2, H3 all the way to G1 Hn, and that's a coset, and we can do this for all the elements of G. Now we're going to prove 3 properties of cosets, and having done that we'll be able to move fairly quickly to proving Lagrange's theorem. So the first property we're going to prove is that every element of G is in a coset. So I'll just write this up here. Every little g in big G is in a coset. And to see this, we just construct the coset again. So let's look at our coset, our G1 coset, and it's G1 multiplied by all the elements of the subgroup H. Now, because H is a subgroup, it will contain the identity. So arbitrarily we'll decide that H1 is the identity. So our coset is G1 H1, G1 H2 all the way to G1 Hn. But H1 is the identity, so this is G1E, and it's just G1. So because the identity is always in the subgroup, we can say that all G and G will always be in the GH coset. So every element of G is in a coset. Now the next result we need to prove is that all the cosets have the same order, and it's the same order as a subgroup H. So the order of the cosets is equal to the order of the subgroup H. And to do this, we need to prove that the mapping from the subgroup H to the coset is bijective, which is to say that it's surjective and injective. So let's do that. So we'll just write the elements of the subgroup here, some of them anyway, down to Hn, and here are the elements of the coset, so GH1, GH3, N. So for the mapping to be subjective, every element of the coset must be mapped to by an element of the subgroup H. And we can see that this is obviously the case because H2 maps to GH2, H1 to GH1, all the way through to Hn mapping to GHn. So this is a surjective or onto mapping. Next we have to demonstrate or prove injective. And for this we need to be able to say that for two elements of the coset are equal, this can, so let's call them GH1 and GH2, this can only occur if the elements of the subgroup which map to them are themselves equal. So let's prove this. So we'll multiply on the left by G inverse, and because of the associativity of group multiplication, we can pair off G inverse and G, which is obviously equal to E, and we find that H1 equals H2. So what we have proved is that the only way that GH1 can be equal to GH2 is if H1 equals H2. So this is definitely an injective mapping. It's also a surjective mapping, so we can say it's bijective. And therefore the order of the cosets is the same as the order of the subgroup. Now we have one further property to prove, which is that the cosets form a disjoint union. Disjoint union. Now what this means is that either the cosets are all identical or they have no elements in common. So putting that into notation, let's take two cosets, so we'll say G1H intersection G2H. Either the intersection is the empty set or the cosets are identical. So let's prove that. Well, first of all, if the intersection is the empty set, then there really is nothing to prove. So the situation we're interested in is if there's an element G, say, which is in the intersection of the G1 coset and the G2 coset. This means obviously that G is in both cosets, so we can then write G as being equal to G1 H1 for some H1 in H, and that will also be equal to G2 H2 for some G2 H2 in G, H2 in H, and this is because G is in both cosets. So now we can multiply on the right by H1 inverse, so let's do that. G1 H1 inverse equals G2 H2 H1 inverse. H1 inverse is E, and just moving up here, we're left with G1 equals G2 H2 H1 inverse. Now moving back here, we can do exactly the same for G2. So this time we'll multiply on the right by H2 inverse. So G2 H2 H2 inverse is just G2, and then we can multiply on the right here by H2 inverse. So this will give us G2 equals G1 H1 H2 inverse. I'll just put that in the box. So just to recap, what we're saying here is that if there is an element in both cosets, in other words the intersection of the cosets, this means that we can write G1 in terms of G2 and G2 in terms of G1. So now what we need to consider is how this affects any element that's in one of the cosets. So let's consider the element x, which is in the G1 coset. So we can write as x equals G1 h for some h, little h in big H subgroup, but G1 we can write in terms of G2 from that. So x equals G2 H2 H1 inverse H. Now all these H's are members of the subgroup H, and by closure of multiplication we can say that their product is in the subgroup H. So we have that x equals G2 H prime for some element of H, big H, the subgroup, which means that x is in the G2 coset. But of course x was in the G1 coset because we chose it to be so. So what we can infer from this is that the x is in both cosets, so the G1 coset must be a subset of the G2 coset. Now you probably can see pretty much where this is going now. Let me make some space. So we'll now consider an element y in the G2 coset. So we can write y as equal to G2 H double prime now, little h double prime in H the subgroup, and again from our expression here we can write y in terms of G1, so H1 H2 inverse H double prime. All these are elements of H, and so the product is an element of H. So we have y equals G1 up to triple prime now, which means that y is in the G1 coset. But of course it was already in the G2 coset, so this gives us that the G2 coset is a subset of the G1 subset, is a subset of the G1 coset. Now it should be clear that the only way these two expressions can both be true is if the two cosets are identical, equal. So what we have shown here is that if there is one element in the intersection of the two cosets, this implies that the two cosets are equal, that they're identical, which is the definition of a disjoint union, which is what we wanted. So let's clear some space. we'll just recap. So we've shown that for all elements of G is an element of a coset. The order of the cosets is equal to the order of the subgroup H, and the cosets are a disjoint union. Now, because every element of G is in a coset and the cosets are a disjoint union, so which means that every element is only in one coset, this means the cosets form what is called a partition of G. This means that we can write G as the union of its cosets. So let's order the cosets here. This is because all the elements are in a coset and none of the cosets share elements up to the kth coset. And now we can write that the order of G is equal to the order of the cosets added up to the sum of the order of every coset. HK. But up here we showed that all the cosets have the same order, and this is the same order as H, so we can now write that the order of G, there are k cosets, so it's k times multiplied by the order of H, and that completes the proof of Lagrange's theorem.